Hello all, my name is Amit Sharma. Today's presentation is centered around a topic named Design and Development of Circularly Polarized Graphene Antenna for Terahertz Applications. This was the work presented in an IEEE conference named Indicon 2021 held in IIT Guwahati. The outline of the presentation is introduction, where I will be discussing about the terahertz antennas of what and why, applications of terahertz antennas, graphenes, what and why. Presented work will also be discussed containing antenna design, comparative analysis and results, and it will be concluded and then the references are also there. Starting with introduction, the right hand side figure is taken from a research white paper from Samsung organization. We see that it shows ultra-fast wireless communication applications, futuristic view. We can see that there are artificial intelligence-based virtual reality devices, Internet of Things-based mutually communicating machines, ultra-fast and high-definition video conferencing is happening here. Fully automatic robot manufacturing units are also there. These are the futuristic applications which will be requiring ultra-fast data transfer, and hence in this era of technological advancement, wireless communication is an utmost part of people's daily life which require ultra-fast communication. Now there are certain things about antennas which are an inseparable part of communication. So specifically concentrating on terahertz antennas because they are being expected the main attention of 6G communication. So let's start with the terahertz band. So the position of terahertz band as per this diagram you can see here is between the microwave and infrared region. We see that this one is the infrared region, this one is the microwave region. Frequency is ranging from 10 raised to power 9 to 10 raised to power 11 hertz, and the infrared range is having frequency range from 10 raised to power 13 to 10 raised to power 14 hertz. So between this range, or specifically speaking from zero point 0.1 to 10 terahertz is the range for terahertz communication or terahertz band. We see several diagrams here. These are the futuristic applications where the terahertz antennas can be very useful. We see that barcode reading is there. We see that microchips are there. We see that there are tablets which are being opened and the inside material is being tested. We see wireless or automobile cars. So these are some of the futuristic applications where terahertz antennas can be very useful. Now the other part of the slide contains comparison between terahertz and other wireless technologies. So we see that there is long-term evolution or LTE technology, the frequency range for which is from 1900 to 2100 megahertz. The transmission range is of 5 kilometers and the peak data rate is of 100 Mbps. So after LTE, there is global system for mobile communication. We call it GSM. So if we want to name it in terms of general terms, so GSM can be considered as 2G, while LTE is considered 3.5G or 4G. So let's talk again about GSM. So we see the frequency ranges from 460 to 1000 megahertz and then 1700 to 2000 megahertz. Apart from that, the transmission range for GSM was from 1 to 20 kilometers, and the speed, or the we can say peak data rate, data transfer speed or the peak data rate is 1 Mbps. It was very small. Then we talk about WiMAX or IEEE 802.16. This also comes under 3.5G or 4G technology. We see that the frequency is higher. It is from 2.5 to 2.7 gigahertz. The transmission range is from 50 kilometers and the peak data rate is 128 Mbps. So we see that the 4G technologies are having 100 Mbps and 128 Mbps data speed. Wireless fidelity or Wi-Fi, known in short, is a technology which concentrates on the frequency band of 2.4 GHz or specific frequency range of 2.4 GHz. The transmission range is typically 30 meters. We know it as the Wi-Fi range, and the speed is more than the 4G data speed, which is around 150 Mbps. Now the other technology is Zigbee. This is a separate technology, IEEE 802.15.4. The frequency range is same as Wi-Fi, 2.4 GHz. Apart from that, two other frequencies are 868 MHz and 915 MHz. We can see that the significant difference between both the transmission ranges of Wi-Fi and Zigbee. We see that Zigbee is having 1 kilometer of transmission range, which is way more than the Wi-Fi. But the drawback of Zigbee is also very much significant. We see that the Wi-Fi is having 150 Mbps data rate, while Zigbee is having 250 kbps of data rate. The other technology is Bluetooth, low energy technology, or we call it BLE. So the frequency range for Bluetooth is similar to that of the Wi-Fi, which is 2.4 GHz, but the difference is in frequency range. We see, sorry, the transmission range. We see 100 meter and 30 meters. So compared to Wi-Fi, Bluetooth range is way more high, and the data speed is also quite different. We see that the Wi-Fi data rate is of 150 Mbps, while the Bluetooth data rate is of 1 Mbps. Now there is low power wide area network, or we call it LORA WAN. Now the frequency range for this band of technology or this band of communication is 868 megahertz, 915 megahertz, and sub 1 gigahertz. The transmission range of 10 plus kilometers sets it apart from other technologies except the WiMAX. Then the data rate is also makes it separate from others. It provides only 50 kbps of data rate, which makes it redundant. Now the other technology is narrowband Internet of Things. Now it comes in the frequency range of 700 to 900 megahertz with the same transmission range as LoRaWAN, and it is 10 plus kilometers, but the data rate is again in kbps, which makes it redundant again. Now there is technology named millimeter wave communication. So this covers the frequency range of 24 to 100 gigahertz, while the transmission range is in 100 plus meters. The data rate is the most significant thing here. We can see that except millimeter wave, earlier other remaining technologies have not given Gbps data rate, but millimeter wave communication technology have shown that it can provide the 10 Gbps data rate. So till now, millimeter wave communication has been the fastest wireless communication technology. But after this, we talk about terahertz communication. Now, this is having the frequency range of 100 gigahertz or zero point 0.1 terahertz to 10 terahertz. And the transmission range is again in 10 plus meters, which is comparatively smaller than the millimeter wave communication technology. But we see that the data rate is way much higher, starting from 10 Gbps to 160 Gbps. So this sets apart the importance of terahertz communication in ultra-fast communication applications. Now, while talking about terahertz communication and terahertz antennas, there are certain materials which are better than typical microwave antenna materials such as metal. So here the topic is graphene. Graphene is a single atom thick sheet of carbon, and it acts like a 2D object, or we can say 2D material. Graphene's properties as shown in table 1, this table makes it a preferred choice for terahertz antennas. We see that there are certain parameters, and on the basis of those parameters, copper is being compared with graphene. We see that the electronic mobility of copper is around 32 centimeters square per volt second, while that of graphene is around 2 into 10 to the power 5 centimeters square per volt second, which makes the mobility of graphene very much higher than that of copper. Now, the mobility is an important parameter while considering or calculating conductivity of a conductor. So it's certainly visible that if a material or a conductor is having higher electron mobility, then that must be providing higher electrical conductivity. So that's why graphene is a better conductor than copper. The other thing is the current density. We see that the current density of copper is 10 to the power 6 ampere per centimeter, while that of graphene is 10 to the power 9 ampere per centimeter. So that is also 10 to the power 3 times high. Tensile strength is another significant property of graphene. We see that for copper, the tensile strength is 587 megapascal, while for graphene, it is way much higher. It is 1.5 terapascal. It shows the strength of graphene. Thermal conductivity is also an important parameter while talking about metals. So we see that for copper, thermal conductivity is 400 Weber per meter per Kelvin, while that for graphene it is around 5000 Weber per meter per Kelvin. So these properties makes graphene a better conductor at terahertz frequencies than copper. Now, while talking about graphene, we are supposed to talk about surface plasma polaritron waves, which are highly confined electromagnetic waves, and these waves are excited at metal dielectric interface when incident photons get coupled with oscillating electric charges. These electric charges are surface plasmons at the surface of the conductor. Now, why we are talking about surface plasmons? Because graphene supports the propagation of tunable and strong surface plasmon photon waves at terahertz frequencies, while other conductors support weak surface plasmon photon waves, and that too at optical frequencies. Hence, graphene is being preferred at terahertz frequencies. So now discussing about the importance of graphene, let's move forward for the other specific properties. These are the structures which are related with graphene. Figure A shows the honeycomb lattice structure of graphene. We know that the graphene is a single layer thick sheet of carbon. So the arrangement of atoms in that sheet, that 2D sheet, is like this only in honeycomb lattice structure. Apart from this, the B figure shows the energy band diagram of graphene. We see that this is the energy band diagram of graphene. This is the valence band, this is the conduction band, and the mid part is the energy gap. We see that in this small part, which is zoomed here, we can see the C. So this C part, the center shows the placement of electron, and this figure C also resembles the conical energy momentum plot of graphene. This conical energy momentum plot of graphene is similar to that of lights. So this kind of energy momentum plot is provided by light also. So this linear relationship makes electrons present at the center, specifically one electron present at the center of these bands, very much mobile. That mobility provided to this electron makes the conductivity of graphene very high. The other important part of discussion is the conductivity and tunability. So graphene's conductivity is being very high. Apart from that, it is tunable also. So complex conductivity of graphene with its constituent parts, interband and intraband conductivity are explained in this paper we see. So the things which we got to know from this statement is that the graphene's conductivity is complex in nature. It is having real and imaginary parts. Apart from that, it is having two parts of its own, which are interband and intraband conductivity. So the graphene's conductivity formula or equation is given by this equation. We see that it is having omega. Apart from that, the other parameters are tau and QE. So these are the variables on which uh, the graphene's conductivity depends. Conditions for SPP waves excitation and propagation on graphene's surface are also explained in this work, and the graphene is characterized by surface conductivity sigma. We see that there are some parameters which are omega, mu c, gamma and t. Here omega is the frequency, so it shows that the graphene's conductivity depends upon frequency. Mu c is the chemical potential applied on the desiccating pad, or you can say graphene. So it depends on chemical potential also. Gamma is the scattering rate we see, and this depend upon tau, which is the relaxation time. Now relaxation time is the time taken between the two consecutive collisions of electrons while moving in the surface of graphene. So this relaxation time vary the conductivity of graphene. Apart from this, temperature is an important parameter on which the conductivity of graphene depends. Now for isolated graphene characterized by complex surface conductivity sigma equals to sigma dash plus j sigma double dash. Here sigma dash and sigma double dash are the real and imaginary part of the conductivity. Proper transverse electric surface wave exists if and only if sigma double dash is greater than 0. We see that the imaginary part of conductivity, if it is greater than 0, then there will be a proper transverse electric surface wave associated with interband conductivity. So when we talk about the frequency range higher than 5 terahertz, the interband conductivity value will be higher, and at that time we'll be calculating or verifying the existence of transverse electric surface waves. While when we talk about the frequency range between zero point 0.5 to 5 terahertz, the intraband part of the conductivity remains active, and for that we will need to prove the existence of transverse magnetic surface waves, which they said that can exist when the sigma double dash value is less than 0. So while fixing a frequency range for terahertz antennas, suppose the range is for intraband between zero point 0.1 to 5 terahertz, if we get the imaginary part of the conductivity of graphene negative, then it proves that a transverse magnetic surface plasmon photon wave is existing on the surface of graphene. Now, here the equation for intraband conductivity is given by sigma intra omega mu c gamma t equals to minus of j q square kb capital T divided by pi h bar square omega minus j 2 gamma in bracket mu c by kbt plus 2 ln of e raised power minus of mu c by kbt plus 1. Here kb is the Boltzmann constant, T is the temperature, omega is frequency, h bar is we see it as some another constant, and apart from that we have discussed about mu c as the chemical potential, q is the temperature of electron. These are some of the variables on which the conductivity of graphene depends. Now another diagram is provided here. We see that this conical structure, and at the center here is the graphene's electron. Now this energy momentum plot is here, and when mu c or the chemical potential is 0, the graphene's electron is at the center. Now by changing the value of graphene's chemical potential, we can move the electron from valence band to conduction band. Here or without the chemical potential, it is at the center. So by reducing the chemical potential, or if it is if the electron is at the center for the chemical potential of 1 electron volt, so by reducing the chemical potential from 1 electron volt to 0.5 electron volt, the electron can be moved to the conduction band or to the valence band by variation of chemical potential. This is called valence band and conduction band. This dependence of graphene's conductivity on the chemical potential makes the conductivity of graphene tunable. This is an important parameter of graphene, which makes graphene based antennas frequency reconfigurable. Now there is a paper by Sasmita Dash, Dr. Patnaik, and Mr. B.K. Kaushik. So the title of the the paper is Performance Enhancement of Graphene Plasmonic Nanoantennas for Terahertz Communication. This is the structure of graphene based antenna is shown there. We see that top layer is graphene, which is placed upon the silica layer, and above below silica layer there is silicon layer, and at the bottom there is ground plane. The concept and analysis of graphene plasmonic nanoantenna over a silica silicon substrate at terahertz frequency is presented in this paper. We see that there is Vg, or the applied voltage between graphene and silicon layer. This one is gate voltage. This gate voltage applied between the graphene and silicon layer provides the variation to the chemical potential. That is important. The performance enhancement of antenna is proposed by controlling the surface conductivity of graphene using an electric field effect. So this is the concept of this work, a very informative paper. Now let's come to the topic, which is the graphene plasmonic antenna design at terahertz frequency, specifically the circularly polarized patch antenna. So the presented antenna is having this dimension. We see that the diameter of the graphene circular patch antenna is 68 micrometers, while there are slots at the end points of the diameter, which are making this circle a circularly polarized structure, so that the antenna can be circularly polarized. The thickness of graphene layer is, we can see that it is 0.35 nanometer, which is a single atom thickness. Substrate used is silica. We see that SiO2 is used. The thickness of the substrate is 10 micrometer, and we see the chemical potential applied for this simulation is 1.5 electron volt, while the relaxation time considered is of 0.5 picosecond. So the simulation of this antenna is done in using CST simulation tool, and this is the structure of the antenna. We can see it. This is the top view, and we can see there is ground at the bottom. In between there is the substrate. We see the substrate as silica SiO2 with epsilon value 3.8. Patch antenna is graphene. So initially it was taken as 10 nanometer. Then we have varied the thickness of the graphene patch. We see this one here, the graphene 10 nanometer, or we can see the thickness 0.01 micrometer. So this thickness is for this is the automatic value of thickness, and which is taken when the graphene is taken as a dielectric, or we can say uh, 3D material having a thickness instead of a 2D sheet. So while considering a 2D sheet, its thickness is automatically uh, one one atomic layer, or 0.35 nanometer. This thickness of 10 nanometer automatically applies when we change the material of graphene from graphene to graphene EPS. We can see here, if I click here and click on change material, so apart from graphene, there is another option of graphene EPS. This graphene epsilon is due to the permittivity, existing permittivity in that material, and the permittivity is there because of the material thickness, which is 10 nanometer. So here for the presentation we have not used the graphene EPS material. As we can see here, we have used graphene material. For graphene material, the thickness is considered as 0.35 nanometer. Now moving ahead, we see the response of the designed antenna in terms of return loss and axial ratio. Since it is a circularly polarized antenna, so we see that the axial ratio is well below 3 dB for 0.5 and 1 terahertz. around, we see that the S11 value is very good at 1 terahertz of frequency. So making it circularly polarized antenna at 1 terahertz. Apart from this, the efficiency and gain plot is also provided. We can see that the efficiency at 1 terahertz is very small, around 14-50%, both the efficiency, while the gain of the antenna is also negative. We can see that the gain of the antenna is minus 2.19 dBi. So the negative gain and very small efficiency makes this antenna redundant. So to make it useful or to improve the performance of this antenna, we have used the concept of another substrate. We have improved the overall permittivity or cavity properties of this antenna. To improve the efficiency of single substrate antenna, it is transformed to silica-silicon dual substrate. We see that the substrate heights are 10 micrometer and 10 micrometer, means both are of the same height. And as we know that incrementing the height of the substrate to an extent enhances the fringing field's radiation, resulting in gain and efficiency improvement of it. So that's what I've said about the cavity. Better cavity provides better response in terms of radiation, and to get better cavity, we have enhanced the height of the structure. Apart from that, the permittivity was an important part. So higher permittivity, lower substrate is enhancing the property of this antenna. Hence, we have used silica as the sturdy lower substrate for the silica above substrate. So this is the dual layer structure of the designed antenna. The CST structure, the same is shown here. We can see that the lower substrate is silicon while the above substrate is silica, above which the graphene patch is placed. We can see that there is ground layer also. The S11 response of earlier single substrate antenna was like this, centered at 1 terahertz, while the dual layer substrate is providing a little shift but terahertz, but approximately maintaining the response or the pattern of the response. We can see the shift is there. The reason behind the shift is the increased permittivity of the overall substrate. By know that by increasing the permittivity, the frequency or the resonance shift towards lower frequency, while the lower permittivity shifts the resonance towards high frequency. That's why we are having a shift, smaller, lower, small frequency shift of terahertz. The axial ratio is also shifted a bit uh, beside terahertz. We can we can see that it is around 38 terahertz. It is due to increment in the permittivity of the substrate. But what is the outcome of response in terms of gain and efficiency? So we that for see the antenna is providing three efficiency of 70 around 70%, while the total efficiency of so this is a performance of the antenna. Summarized outcome. Actual issue plot is there. See and efficiency as the radiation efficiency plot is much higher higher means constantly remains constant to 3 to 4 dBi going up. This significant improvement in the performance of the antenna, graphene terahertz antenna, was the radiation 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 pattern pattern or response, we can the design was further improved for chemical potential. We see that the gain at 1 terahertz of frequency is around 4.329 with the efficiency going up to radiation efficiency going up to 85%, while the total efficiency is going up to 63%. So this improvement in the antenna performance with chemical potential is what makes graphene antennas very much flexible in terms of frequency as well as gain response. By improving the or by increasing the chemical potential of graphene antennas, its performance in terms of gain efficiency can be improved. This is a slight performance comparison of the designed antenna with the existing graphene terahertz antennas. There is an antenna in which the resonant frequency is around 5 terahertz. We see that the directivity is around 5 dBi, while our antenna is providing the directivity of 6.6 dBi. Secular polarization is there. Gain is around 4.32 dBi. S11 lowest value is minus 18 dB. The radiation efficiency and the total efficiencies are also significant. Actual ratio below actual ratio bandwidth at 1 terahertz is around 100 gigahertz. That is also significant. Apart from that, there are some other separately polarized antennas also. We see that there are sub terahertz 0.35 terahertz circularly polarized antenna. We see that the gain is very high. Both the antennas are having 10 plus dBi gain, but there are some other things which are missing, such as this efficiencies and directivity. Axial ratio bandwidth we see are also very small, around 27 gigahertz or 54 gigahertz. So there are some drawbacks or trade-offs while designing the antenna. Again, this makes the graphene terahertz antenna and a very interesting topic for research. These results calculated so far are not the best we can have from a graphene-based circularly polarized terahertz antenna. It can be improved further with precise impedance matching. There are some circularly polarized terahertz antennas in literature, but their shape, size, frequency range, and material used make such antennas useful for some specific applications they are designed for. Hence, designing a graphene-based circularly polarized micrometer-sized for interchip and intrachip applications, plasmonic terahertz antenna was a target, and we have achieved it successfully. These are the references which we have used for this presentation. Thank you so much.